Hello everyone, Nubosaurus here, bringing you another update on the SkittleBits project. So far, a lot has changed since the last update, I'll tell you that. And a lot of the changes actually have to do with the features involving 1.9, because that is now officially out. But basically, the first thing I did here since the last video is actually move the entire computer system to a void world. And the reason for that is because I've noticed 1.9 is extremely framey. It's also quite memory intensive. We seem to be sitting fancy at 50% memory usage right now. But when I've got this... wrong button. When I've got this thing running, it'll chew through all of its reserved memory very, very quickly. So, and that's not something that used to happen. Prior to the 1.9 update, I was able to run projects like these very, very smoothly with very, very minimal frame rate issues, and very rarely would I ever go above 80% of my memory usage. So, I know it's a change in the 1.9 code. Because I know my computer can actually handle stuff like this. But anyway, so I moved it to a void world to try and reduce lag. Unfortunately, it's still extremely laggy, which is why I have the system off right now. Some other changes that have happened is I've actually relayed the entire architecture just to try and make it a little bit more intuitive to navigate, as well as cleaning up the wire a little bit, making it a little bit cleaner and compact. The other things that have changed, I've added several I/O peripherals, and several more still need to be added, but I'll get to those in a sec. The first thing I want to show you is the RAM has been reduced in size, seeing as how my computer can't handle a kilobyte, excuse me, can't handle a kilobyte anymore. It's been reduced down to 32 bytes. Which is still, a pretty decent amount of program memory. Just means that you can't store a whole lot of stuff in memory. My hopes was to give this computer the power necessary to hold several stacked frames, variables, and of course your main program, all in the same memory bank. But unfortunately, seeing as how it's a little smaller, your program and stack should still fit in there just fine, but as far as variables are concerned, you can only fit them in the computer itself, unless you're extremely efficient with your memory usage, in which case maybe, but other than that, you're probably limited to 3, maybe 5 variables at most. The other thing that I want to show you is the programmer interface, or user interface. So this doesn't actually give you any means of communicating with the computer. I actually plan on adding an I/O bus for that. Just some general purpose I/O pins on this side to interact with, so that would be your computer interaction. This is basically just memory interaction, as well as some basic CPU interaction. So above here we've got a display which displays the address selected, and when the computer is in program mode, this display will display what's in that current address. So in this address is 87, which is a halt instruction. And like I said, it's a little laggy, but you can change the address by punching it in here. It's a 16-bit address, so we have A15 through A0. So you can punch in your new address, and you can hit jump, and it will take you to that address. For example, I guess right now it's selecting 0, so if I were to hit jump, we'll actually jump to address 0, and we'll see what's in the data location 0. So now we're at 0, and the memory in location 0 is D0, which is correct. I actually have a program written down right here. So that is what's in address 0. And then of course you can change what's in the address using these lines, and then you simply hit enter, and enter will auto increment to the next address. The only problem with that is, of course, if you ever want to review your code, you need to re-enter the code in the panel before moving on to the next address, because as it stands, there's no way of incrementing to the next address without modifying the content. and then but you can decrement without modifying, so that's fine. And then the other mode that you have is step. Obviously step won't work at this point because the computer is halted, but if the computer was running, you'd basically set this to program, then you'd set that to step, and then you just hit this button to step through the program. And yeah, you could observe the effects of that, or fly around and physically watch it happen. It doesn't matter. But yeah, and then once you're done programming, flipping this lever back up will automatically reset the computer, bringing its selected address to 0, and resetting all the registers and everything. I'm not going to do that because that would start the computer, and I don't want that to happen. Because, like I said, it's extremely laggy. So I'm just going to leave it like it is. You'll just have to take my word for it. Hopefully, just on an off note, hopefully Mojang fixes the lag issues relatively quickly, but for now, I'm dealing with it, I guess. Anyway, like I said, even though everything's been rearranged a little bit, everything is still here. We've got the interrupt control module there. We've got the memory address control module here. We've also got a few extra I/O. So down here is a variable clock speed selector. So basically what we've got is we've got a single clock source here, and it actually goes through a series of T flip-flops, which is effectively a counter, or a frequency divider, depending on how you're looking at it. In this case, it's a frequency divider. And then we have a register up here, which allows us to select one of the 4 frequencies that are produced, and feed that into the computer system. Each frequency is exactly half of the preceding one, so this is half of the clock speed, this is a 1/4 of the clock speed, an 1/8, and a 1/16. So this allows for a little bit of control of the speed of the computer. If you're a little laggier in Minecraft than I am, you can select the divide by 16, no problem. Your computer will, or this computer will run extremely slowly, but it will reduce lag tremendously. I tend to keep it on divide by 2 because I'm more of a get it done quickly kind of person. We've also got a random number generator over here. By the way, all of these things are individually addressable. So that one was on address number 1, and of course the memory address control unit is also on the memory map, or the I/O map. So that is address 0. The frequency selector is address 1. The random number generator is address 2. And as it says on the tin, it generates random numbers between 0 and 255. Then we've got a few more I/O stuff. We've got 2 timers, 2 16-bit timers. The first one, and I believe this one is on memory or I/O address 3, I think. This one is just a timer, and excuse me, at least I think this is it. No, sorry, this is the watchdog. This is on address 3, and this is the 16-bit timer. And the way this works is it basically just keeps track of the number of clock pulses that the computer has received since the start of the program. And if you ever want to request it, the first read will sample and present to you the high byte, and then the second read will present to you the low byte, and then it will resample the next time you read from it. So that just ensures that you're always getting an accurate reading, more or less. I mean, it's going to lag a little bit by a few clock cycles, but that's no big deal. And then, of course, that can be brought into the CPU via the central bus. The other timer is a watchdog timer, and this one works a little bit differently. Basically, you give it a 16-bit value, high byte first, then low byte, and it stores that in this 16-bit register up here, which is then compared with the 16-bit counter down here, and if they're equal, it will send out a equal signal, which then will deactivate the counter and send out a watchdog interrupt, and this will actually be tied to the interrupt module, so that the computer can know that the watchdog is signaling for an interrupt and execute a interrupt service routine. Yeah, so that's all the IOs that I've added so far. That one's on IO address number 4, I believe. I'm still planning on adding other IOs. I want to try and add digital GPIOs, as well as some sorry, did I say serial? No, parallel GPIOs, serial I/O. I was thinking analog or even PWM, but that's getting fancy. And then I also want to add a interrupt mask. So as it stands, the CPU has its own internal interrupt mask, which basically just ignores any interrupt requests coming on the pin, interrupt request pin. And that basically just shuts off all interrupts, but maybe you want to shut off certain interrupts, but not all of them. So I want to add a register or something that can mask individual interrupts. And I figured, you know, we can mask up to 256 with an 8-bit address, but since we've got 8, we've only need 3 pins or 3 bits to actually mask or unlock certain interrupts. So I guess 4 really, because 1 would be the mask or unlock kind of bit. But yeah, that's one of the things that I want to add. So it's IOs and then the mask, and then we're pretty much done with the system. I basically just need to pretty it up a little bit. I want to get the central bus kind of color coordinated so it matches the SkittleBits layout. Maybe not everything else, but at least the bus. And then I do need to do some documentation. I want to try and thoroughly document schematics and explanations for the CPU, as well as instructions and instruction sets, and then I want to fully document this entire system right here so that anybody who gets their hands on this can fully understand what's going on here. And then I guess last and kind of the least, really, the last thing I want to show you here is the expansion bus. This thing is expandable. You can add as many I/O peripherals as you like, so long as the address never exceeds 255. But we do have an expandable I/O bus, which is awesome. Well, actually, it's an everything bus. It's just a general control bus. So on the bus, we've got data in and data out, which go directly to the CPU. These allow for well, data implantation and extraction from I/O. Then we have the actual I/O address bus, which is an 8-bit bus, allows you to select different IOs. And then up here is an 8-bit control bus, which includes things like the read and write cycles, or read and write pins, sorry, the ALE and IO memory pins, clock, wait, reset, and servicing interrupt pins. And those are basically just flags from the CPU which give the rest of the computer an idea as to what the CPU is currently doing. And then the clock is, well, yeah, just the clock. Except for the wait, I should say. The wait is actually a line that any I/O can hook up to let the computer know that it's not quite ready to send out its data. So basically, if something's a little slower than everything else, you can hook that up to the wait line. And on T2 of the internal clock cycle on the CPU, it will actually sample the wait pin, and if it's on, it'll actually stop its process until the wait pin goes low. So that's just a way of keeping the clock speed high while still maintaining synchronicity with slow I/O peripherals. So yeah, that's everything. Like I said, that's all the changes that I've made here. And I've still got a few, like I said, a few more changes to go. Still want to add those I/O, the mask, and of course the color coding of the expansion bus. But other than that, this thing is coming along very, very nicely. I'm super excited to get this all ready to go. And like I said in the last update, I already have another project in the queue ready to go as soon as this one's done. So I actually have some motivation to get this done. But yeah. Other than that, that's everything I wanted to show you. So hopefully you enjoyed, and I'll see you guys in the next video. Bye!